Okay, folks, I don't think anyone should be too surprised about what's coming next. We just finished particles in 2D space for static mechanics. Well, we're going to add another dimension there. So I alluded to this or mentioned it directly the last time, but vectors in 3D space really hard to do graphically. So you're pretty much going to be limited to decomposing your vectors, your forces, into a Cartesian coordinate system, into its various components, and then working from there. Because some simple 3D vectors are decent enough to do, on their own, but once you start adding them together, or God forbid, taking a moment, which we'll get at later, it really doesn't work. So you might also be given basically the angles between the original force and all the three axes. Or directly told the directional cosines of those. And basically the thing to keep in mind here is that when you're taking those measurements, measuring those angles, those are basically measured off of the axes in question directly. So, in this instance here, it's it's based upon the it's kind of based upon the angle at its smallest portion. It's the angle directly between these two, and not necessarily the same as that angle, and it's not necessarily the same thing as if you were measuring a projection of this force down onto a different plane, and then measured. The plane upon which you're measuring this angle is a plane that contains the origin, this A point here, and some point along the axis in question. But anyways, so when you take those measurements, it gives you a unit vector, and just based upon those cosines there. And then once you plug everything in here, that'll give you a unit vector. Again, all of these combined are going to be equaling up to unity for a magnitude. So it will be a unit vector. Combine all these together using Pythagoras' theorem, you're still going to get a 1 as your result. Another thing that might occur is you might have been given the location of 2 points in space along which that force acts. And you can use the displacement vector between those 2 points. So in this graph here, it's the points are m and n, and so the displacement vector in that case would be mn. If you use that displacement vector, since the force acts kind of between those 2 points, they'll have the same unit vector as the force will. So you can use those points in order to determine the unit vector for the force in question. So basically, we'll have these dx, dy, and dz. That's just the displacement along the x-axis between m and n. The displacement along the y-axis between m and n, right here. And the displacement in the z-axis between m and n. So from here to here. Keep in mind that those values can absolutely be negative. Displacements can be positive or negative. They're not necessarily distances. So you need to keep that in mind, because if you mix up the sign on one of these, then your unit vector is going to be pointed in the wrong direction. And if you mix up the displacement, the z-axis displacement here, then this thing will be kind of coming out towards us instead of kind of into the page. If you mix up the y displacement, so you're switching the sign on your j on your j's there, then instead it'll be angled downwards. So you're going to get an incorrect value for that. So measuring those, basically our unit vectors just ends up being the displacement in x over the total distance between these 2 points times I, displacement in y over the total distance times j, displacement in z over the between those 2 points times k over d. And again, our d is going, our d value here is just the magnitude of the distance in space, or the displacement in space between these 2 points. And again, that particular value has to be positive, because we're squaring every term that goes into it before we're taking the square root. Again, using Pythagoras' theorem. Then, okay, we've got our vectors. We know how to break them up into their components. And again, why are we doing this? Because we want to be able to figure out the equilibrium for those particles. So again, it's not really all that more complicated. Previously, we knew that the resultant for all forces on the particle needed to be 0, so we were able to calculate this, and we were able to calculate this. Now we just have to add this third term in here. That's not, it's a bit more tedious, a bit more extra steps in calculating, breaking out the forces into its other components, but at the end of the day, you're doing a bit of multiplication, you're doing a bit of addition, subtraction, etc., and it all comes to 0. It's not necessarily any more complicated per se. But I will say this thing: a proper free body diagram is going to be critical in order to make sure that you're kind of keeping all your signs correct. So you need to have a nice clear diagram, possibly with multiple orientations upon it, so different views that can be used to properly situate the forces in question, in order to make sure that you're accounting for the forces in question, including their signs. And beyond that, same process. That's about it. That's about all there is to do it. Break up all the forces that are acting upon the particle into its 3 components now, and then just add those components for all of the forces that are acting upon the particle, and if they're at equilibrium, then they will add up to 0. That's about it.